All right, everyone, welcome to the lecture series on thin layer chromatography. Thin layer chromatography is actually followed by an abbreviation, and that abbreviation is going to be called little TLC. And that little TLC does not mean tender loving care, even though you want to give these little TLC plates some TLC when you can, because that way they can make sure that they are going to be working for you. So little kisses are appreciated and little hugs are appreciated because these plates need that sometimes. Don't forget about them. Don't hurt their feelings. But at the same time, we're also going to be talking about the HPTLC version. And the HP is not Hewlett Packard, folks. That's your printers. The HP is going to stand high performance. So high performance liquid chromatography, that is a thing in a laboratory setting. But that is called HPLC. This is not HPLC. This is HPTLC. So high performance thin layer chromatography. So the HPTLC is actually some instrumentation, and the instrumentation is going to be able to do a lot of the thin layer chromatography applications for you automatically. So we're going to talk about that as well, because guess what? Our name says chemical technology, so we need to make sure that we talk about the technology portion, even when it concerns little bitty kind of special TLC plates that we were doing 50 and 60 years ago. So the technique and the types of things that we can do with TLC plates today because of HPTLC has really just completely changed the discussion that we have with TLC altogether. So let's just kind of go ahead and get started. We need to talk about what TLC is all about, and I need to give you a rundown of the basics of TLC first, and then we can kind of sprinkle in some of the instrumentation along the way. All right, so first off, I guess that we can say that TLC is going to be this idea that, oh no, my smooth draw is not working properly. So TLC stands for thin layer chromatography. That's what this is all about, and this is really what we're going to have to start talking about as far as the way the development goes. So thin layer chromatography finds its own little home in a laboratory setting, and the reason that it does find its own little home in the lab setting is because it is somewhat special, it is somewhat unique, it is somewhat different than the whole idea of what chromatography is going to be throughout the rest of the semester. So thin layer chromatography goes by another name, and that other name is very often called planar chromatography. So PLANAR, planar chromatography, is kind of an old school term that we used to use back in the day when we were developing these plates in a laboratory setting. And the reason is because they are developed on slides, and this is kind of how this whole field got started, and these slides were very, very flat. So when you talk about the plains of out west, you're talking about typically very flat levels of land, and this is a very flat level of chromatography, and that's happening on the surface of a plate of some sort. So a very, very flat surface, and if I draw the plate to the side, you know, okay, so here's the plate, there we go, and there's a little bit of stationary phase that covers the surface of that plate. That plate does not have any hills, that plate does not have any mountains. You can't go on snow trips on this kind of particular type of plate. It is very, very flat, so hence the term planar chromatography. And that's kind of still used today by some old school folks that are still out there, and there are some out there, of course there is, that we can call planar chromatography, and they will use that, but now we really call it TLC, and that just means thin layer chromatography. So it is one of the few types of chromatography systems that does not use a column. So a column is something that we've talked about in the previous lecture, and in that lecture we were talking about how the column operates and what happens, and stationary phase and mobile phase and retention times, and all of that is going to happen here as well. There is no difference, but the problem is that it's not really a cylindrical type of tube that we are putting these samples into, or the stationary phase into, or the mobile phase into. Again, this makes it very unique. So no column is there. It is a flat surface with a flat level of stationary phase. So things are going to behave a little differently with TLC, and that's why we kind of devote some time to it here. Of course we're going to, because it is somewhat unique in its own way. Now, this column is not going to be used, but all of the ideas are still going to be there. So we can still talk about stationary phase on the plate. We can still talk about mobile phase on the plate. We can still talk about the way that things are retained on the plate. So all of those calculations that we just went through, all of those discussions about basic chromatography, those are not going to go away. They are still here. They're still at play, and they're still very true. So I don't want you to think that everything that we learned in that very first lecture is all for nothing, because no, that's not the way this is going to work. This is great. So it's going to actually feed into this a little bit, but I just need to start with the one that doesn't use the column first, and that's very often why we start with TLC at the beginning of the semester. These plates, that's kind of what we call those. Instead of columns, they're going to be on plates. They can be made up of a glass backing, and these are very good for a couple of reasons I'll talk about in a minute. They can also be plastic, and they can also be like even aluminum in some cases. So there's different types of backing that's on the plates that we will need for this chromatography type of exercise or technique that we're getting ready to describe. Now, the problem here is that the glass, folks, is very expensive. Ching, 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 money, money, money. All right, so that's very, very expensive. And when I say expensive, you'll see the price tag of what we will pay for maybe 50 plates altogether. And they're not very cheap, and I hate and I cringe and my teeth grit every single time that I have to place this order. But the good thing about the glass plates is that they are very stable. And when I say stable, what I mean is that they're very hard to damage. So I can grab them and I can use them and I can transfer them from one area to the next without any issues at all, because that surface is very rigid and it's very stiff and it's very, quote, stable. So it's very hard for me to break them. It's very hard for me to bend them. And because when I do, I'm actually disturbing that very thin coat of stationary phase that's on the surface of that plate. So that's a good thing about glass plates. And because of that, these are going to be the most common types of plates that you will see out there on TLC and HPTLC. Next up are plastic, and the good thing about plastic is that they are fairly cheap, all right? So I'm just going to do one ching here when the glass had ching, ching, ching up at the very top. So the plastic are very cheap. The problem, though, they're very easily damaged. And this is a problem that I have because I don't want to handle them and accidentally bend them, because if I do start bending them or twisting them, maybe just so much that I just don't even realize that I'm doing it, but it's happening, then I'm damaging the stationary phase on the surface of that plate. And that's something that we can't allow to happen. That stationary phase has to stay the way that it was made. We cannot damage it. We cannot crack it. We cannot flake things off of that stationary phase. That is a bad thing. We don't want to do it, and we need to stay away from it. And plastic backing plates allow me to do that a little bit easier. So even though they're cheaper, they're just not ideal. And the reason is because I can damage them very easily. Next up are aluminum, and then here I'm just going to put ching ching, okay? So aluminum is not expensive like glass is. It's a little bit better step in the right direction. The aluminum is a little bit more expensive than the plastic, but still it's not unreasonable like the glass ones are. So just a tidbit more expensive possibly. And then on top of that, the aluminum is actually going to be a problem. And the reason is because it's the same problem as the plastic ones. They are very flexible. They can be at least. And I can twist them or accidentally turn them or do some damage onto the surface of that stationary phase. And I don't want to do that. So even though the aluminum here is okay, it's going to be a problem still, just like plastic is going to be. The reason that the aluminum is an option is because the plastic ones do not do well in very organic types of solvents. They never have, they never will. So anytime I'm using straight up organics, I need to keep those away from the plastic materials that are used in a laboratory setting. And whenever we can, we go to glass for that reason. So glass is going going to be very stable according to the organic solvents that we're using. And that's also why aluminum is a choice. And the aluminum is there because if you do have plastic back silica and you're using some type of organic that can react with that and maybe destroy it even, then this is going to be bad news when you start dunking those plastic tank or those plates into a tank that's filled with an organic solvent. So for that reason, aluminum comes out and we get that choice, and that's great and that's good. But again, glass is where it's at, folks. Glass is where it's at. So that's what you're going to see most often. That's what we're going to use in our laboratory setting, even though that these options are still out there. So the only chromatography setup that doesn't use a column and it uses a plate instead, hence planar chromatography. And the reason it's called chromatography is because, folks, it still uses our stationary phase. This is still a thing, and it still uses mobile phase. That's still a thing as well. So those definitions do not go away. The mobile phase moves through the stationary phase, and it helps separate our compound components one by one by one. The stationary phase is something that's kind of stuck, and what we've been talking about here is it's stuck inside of a column, but now this is stuck on the surface of a flat plate, so it's still there, it's not moving, so hence the word stationary, and this is going to allow our molecules to interact, or our samples, components that intersample, are to interact with the stationary phase that's on the surface of that plate. So it's still chromatography for that reason. We still have the same theory of mobile phase that's playing. We still have the same idea of a stationary phase that still goes on. But there's actually an extra phase here that the other ones do not get included, and that extra phase is called a gas phase. Oh no, you're just changing it all on me. I just went through a couple of weeks learning what stationary phase and mobile phase was, and now you're changing it and you're saying there's a mobile phase now. Well, yeah, there's a gas phase. That gas phase is going to be important. That gas phase is really somewhat unique to HPTLC, which again is what stands this out, HPTLC, which makes this stand out above the rest. So we need to dive a little bit deeper into this concept of what a gas phase is all about. Talk a little about it. What does it do? What does it interact with? Why is it there? And then really kind of describe why we don't really see those on the other chromatography types of exercises or protocols or lab procedures that we will use with those chromatography pieces within the system. All right. Before I let you go with this video, though, we need to talk about some things that are going to be maybe some problematic things with HPTLC. First off, TLC was used because it was very easy, right? It is super cheap and it is super easy back in the day in order to get this. All I needed was a little flat piece of glass. I needed some silica, and we'll talk about that as well, and some binder that makes it stick. And then I just apply my samples and just drop it into a container or whatever container that might be. So this was very easy to use. It was very easy to train other people on what to do. So this was the great thing with TLC, and it's still the great thing with TLC today. But the problem is that I could not get reproducible results. And reproducible results are going to be a problem because I need that in today's laboratory environment. I need to be able to run samples, and I need to be able to do it sample after sample after sample and get the same result time after time after time on different days, on different humidities, on different temperatures of the rooms. I need it to be controlled. And the problem with TLC is that it was very hard to reproduce. So what that means is that in a laboratory setting, I could go in and grab a TLC slide, and I could draw my little line, and I could apply my sample, and then up and away, there it goes. And then on a different day, I could do the same thing, get a slide, and then up and away it goes. And then what will happen is that on these two different days, I could actually see this sample travel at a different rate, and it will reach a different height. So when I go through and calculate what we call a retention factor of this type of thing, that's how far it travels up the plate, that retention factor could be a number on day number 1, and then 3 days later I'll calculate another RF, and that is a totally different number that I'm going to see, even though it was the same sample, even though I used the same mobile phase, even though I used the same slide. Everything is there, everything is kind of legit. But the problem here is that these data points are not going to be reproducible. And we had an issue with that very early on with TLC, and we still honestly have issues with it if we do TLC in a manual way. So that manual version of TLC, we still have this problem. Now, we can control it a little bit better by using some tips and tricks, but at the same time, this is not really ideal at all. So when TLC was first kind of getting done, it was all done by hand. It was all manual. These were problems that we were seeing, and there were too many variables, right? And those too many variables were things that we could not control. And those led to constant changes of RF numbers. And we'll talk about what these RFs are going to be a little bit later in the lecture series, or the variables are going to be that changes RFs a little bit later in the lecture series. Now, over a course of time, we kind of hit home with TLC, and we wanted it to be better. We wanted it to get the attention that it deserved, and hence HPTLC comes into play. And this is going to be the instrumentation that we will be using in the laboratory setting that streamlines this much better, that gives us more reproducible results, that things look better, things image better, things separate better, and it's all due to the HPTLC instrumentation that we can now utilize in a laboratory setting. Again, the HP stands for high performance, and that's thin layer chromatography. So what you're seeing now is that companies like the USPNF, which is all pharmaceutical driven regulatory stuff, and if you've taken our CTC 115 course, we've went into drastic detail with our USPNF discussions. They are actually including now at this point, finally, HPTLC technology. So they are going through and they're saying, listen, we need you to get on board. We are going to be improving TLC. We're going to be utilizing maybe a little bit more of it. And we are going to start placing in the reference books HPTLC technology on how to do the job, how to do the separation, all of the variables that made this thing problematic. We're going to control them, and we're going to tell you what you need to set your instrument to, so that way we can get better reproducible results. In addition to that, TLC back in the day was not quantitative. And what that basically means is that I can't do numbers. The only thing that I can do is just really ID sample components, nothing more. So I can say, yes, that is aspirin, or yes, that is cocaine, if I was doing this in a forensics type of laboratory. But I could never really tell you how much. I could just say, yes, that is present, or no, that is not present. That's all that TLC was basically good for the most part, especially in the very early years of its use. Now with the HPTLC instrumentation, we can ching quantify. Yay! That means I can do calibration curves, and I can do calculations, and I can kind of figure out how much is actually there in my samples, and not just the identification piece of the samples. So HPTLC technology has really turned this field of TLC on its head, because now all of a sudden I can do things that I normally could not have done maybe just a handful of years ago, and that is quantification on a TLC plate. So that's going to stop this video. In the next video, we're going to continue on with here, and we're going to talk more about the basics of TLC, kind of get a good feel of what this thing is going to be all about before we go into major details of the instrumentation piece. So stay tuned. There's going to be many videos. You know me by now. Of course you do. You know there's going to be like 165 videos for you to watch, and this is just one of many. So you are nowhere near done. So just hit the play button on the next one and just keep keep on a truckin'. I know you can do it. I mean, if you were in person, you will be spending an hour with me. And right now, you've only spent about 15, 16 minutes with me. So just come on back. Keep watching. Keep cranking these things out. You'll be not sorry.